Hi.
And welcome
I'm
back. We have this wonderful guy with us. Hey, how are you doing?
Yep, good, thanks.
So, for everyone who doesn't know him, this is Hugh. Hugh is one of the very first people I met in the Hex community way back in the day. He says he's been working with Hex for much longer than he cares to or is capable of, for that matter, remembering. So, I guess we're all growing up here. He's the primary author of the HXCPP backend and the enemy Haxe library now. With Hugh, you always have to read the names of his acronyms out loud. It's gonna give you a fair share of laughs, I guess. He's just started a new company that the name, when I read it, it looked rather inconspicuous, and I just said it out loud to myself. And the company is called CYENCY. So, um, yeah, just that's a little thing he has. And other than that, we're looking forward. How has time treated you over there, Hugh? How are things in
Yeah,
Australia?
I've managed to stay busy. I've been working from home for a couple of years now, so no real changes for me. Life in Perth is actually reasonably normal at the moment compared to other places. So, plodding along. Haven't had a hell of a lot of time for hacks. I've been busy doing a whole bunch of other stuff. So, if anyone's noticed missing responses to pull requests or something, it's still on my mind. I just need to find some time to have a go at it.
Oh, well, that's, I think, the same for anybody. Anyway, we
Yeah.
appreciate you being here. So, without further ado, here is your stage.
Thanks. Yes. So my talk today is getting hacks into your crevasses and crevices. I guess depending on the size of your crack. It'll be a bit different today. I'll be talking about some of the uses of HXCPP or hacks in general, rather than specifically about the HXCPP backend. Um, so I'll just be going over things a bit differently without a lot of necessarily new new discoveries in HXCPP, mainly because I haven't made any because I've been just, I don't know, doing other stuff. So I guess the theme here is how you can use hacks in a project, but you don't necessarily need to use it for the whole project. Um, you should always use the best tool for the job, and often the tool is hacks, but not everything can or should be written in hacks. It's a multi-target language, so it's good to celebrate the different targets and use as much of it as you can. Um, so this talk is a few ideas about mixing hacks with other ecosystems. So the first thing I'm going to talk about here is a little project I did with a little GUI running on a Raspberry Pi. It was written with Haxe and NME as a little motor controller. It uses OpenGL to render the screens, the buttons, the sliders, the camera view, and the buttons send the command over two serial ports to microcontrollers, and the various information, positions, and forces come back over the same serial links. The serial thread loops are written in native C++ rather than in Haxe thread. This is primarily to avoid issues with stalling on a GC collection, which could be in the order, I guess, up to maybe a few hundred milliseconds, and we don't really want to miss anything in that time. So the point here is, I guess, one of thread isolation. And when Haxe or HXCPP interacts with a foreign thread, you have a few options. Haxe can call into a foreign function, in which case you can use GC free zones. Foreign thread can call into Haxe, in which case you can attach the thread. Or the magic third option is neither system actually calls into the other system. It just sets a bit of data somewhere. And this is what I've used for this in this particular case. So to mesh everything together, I use the metadata, the cpplnclude pattern, which is quite powerful and actually is a bit of an easy way for joining code, getting CPP to call into foreign code and it calling back into CPP without really needing to mess around with much in the way of a foreign function interface. The implementation code here, generated on the right here, is a schematic of the generated code. First thing it does is includes the standard HXCPP generated headers, in which are declared the various functions and variables of the Haxe class, like some Haxe func here. The next thing it does, it will include the file that you've tried to inject with your CPP include call. And afterwards, and here is the blue box is an example of the code that might be injected. Some complicated dependencies and some private functions. But you notice here that this C function can call into the Haxe function because it's in the same file. It can see the definition. So there's not really a problem calling in that direction. And then after it's included the CPP include file, it comes back to the normal Haxe class implementation. And this implementation now can see the injected code as well. So he has no problem calling into the injected code. So the CPP include file is put into the sweet spot between the header file and the implementation and allows the code to be called, one to call the other and the other to call the one. So in this particular example here, I'll just go back. We can see that the file here has a bunch of static functions which can be called from outside the file. They all trampoline straight into a native function. The native function is implemented in the CPP file, and all it does is set a variable and then returns. So it doesn't actually run any code, so we don't have to worry about threads. This technique is pretty useful for all sorts of integrations. I'll come back to that in a minute. So if you have a look at the division of labor here between Haxe and non-Haxe code, most of the code is Haxe, written for Haxe NME, doing the UE and the sliders and the camera feed and various things like that. It's cross-compiled from Windows to Raspberry Pi, so it's quite fast to develop, and being fully hardware accelerated, it's also fast to start and fast to run. There's some good reasons to use Haxe, and the good reason not to use Haxe is the real-time communication with the serial port allows the code to be run without concern for GC pauses. So give it 95% Haxe for that particular case. So here's another similar case with iOS integration. Again, I'm using the CPP include trick to inject, in this case, it's the app11 iOS file into my Haxe class. When I compile the Haxe code with the dobjc define, it generates all the files generated are no longer CPP files, they're .mm files. This is the objc++ classes. These are a superset of C++, so the code happily lives inside these files, but the result is that it can actually end up calling into objc files. So in this particular case, I put all the API calls into this one.mm file, then I inject that whole file into my CPP generated file, and then call functions in this API file quite naturally from the Haxe code using some standard externs. In this particular case, I've added the file XML tag to inject this tag equals enemy Haxe metadata into the file, into the build system, and doing so means that when it compiles this generated file, It'll also include all the compiler flags and header files that come with that are generally associated with NME, which is some headers into the iOS system and native NME types like images or whatever you want to use. So here, when it comes down to like the split between Haxe and non-Haxe for this project, again, it is almost all Haxe really. And why have I used Haxe? Because writing a game, everyone's going to want to use Haxe. Why wouldn't you? Why haven't I done it all in Haxe? This is because to get an Objc example from the internet, I can just grab it, paste it into this injected file, and just edit it properly in there. It all just sits in the one file, and I can then just call into it from Haxe. So it's quite a nice way of working, combining these two things together. So the next example here I have is one of JS Prime. When I was working on NME, I was looking for a web or HTML5 backend. I'm intrinsically lazy, so I was looking for an easy fix. I don't want to write a lot of new code. Ideally, the behavior would be very similar from the desktop and also the browser. I don't want to have two sets of bugs. I just want to have one set of bugs. There might be big bugs, but still only one set. So the first thing I tried was just compiling the code straight from using HXCPP and the WebAssembly WASM output, mscriptum compilers, and it did work. Worked reasonably well. There are a few little things you've got to do with floating point alignments, and the fact that stacks go backwards. But apart from that, it worked. But it wasn't very satisfying because it doesn't take advantage of some of the good things about JavaScript, which is the fact that it's fast to compile, and Java code runs pretty well in the browser. And if you're going to take a second level back from that, you're running code that runs sort of inside the browser. It just gives you an extra level of an extra level of slowness, which I guess normally you'd make up with C++ because of the fixed memory models, but then running my own GC on top of it is just going to slow everything down. So I came up with a solution that works pretty well. First is to compile the NME DLL, which is native C++ code, with WASM into a JavaScript assembly blob, and then compile the normal Haxe code to plain JavaScript. And the JavaScript can call into the NME DLL just like desktop code can call into NME DLL. And so this solution largely avoids my HXCPP code altogether, although it does use the build system to build the NME WASM file. But I can live with that because it all pretty much works. That is, it almost works. It was almost too easy, but there is one fairly large problem, and that is the NME code relies on finalizers to clean up the native WASM resources. So if you can see this code snippet here, I create a shape, do some stuff to it, render it off to a bitmap, and then just let it dangle and just ignore it. Normally the CPP garbage collector would come along and clean up the resources, but JavaScript is reluctant to give you a finalizer. There is some talk of it, but there were some security concerns, and also I think it reserves the right to basically never do a garbage collection if it doesn't really want to. So the finalizers aren't as aren't as deterministic as they are when you've written your own backend and you know exactly what's going on. So the solution here is that the NME display list holds a reference count on the C++ code, the C++ code being the code running in the WebAssembly. So if you make an object and stick it on the stage, like you've called add child onto the display list, then it's safe. Everything's good. Everything doesn't need to go anywhere. If you haven't put it on stage or you take it off the stage, and the C++ reference count goes to 0, the resource objects puts itself on a cleanup list. At the end of the frame, if the object hasn't been re-added to the stage, it checks to see if it has a Haxe owner, a JavaScript owner. And if it does, it serializes itself into a JavaScript byte stream and stores itself in the JavaScript object itself. If it doesn't have a JavaScript owner, then that's fine. It just deletes itself, and we know dangling references from Java code, so that's fine. If later on the JavaScript object actually does need the resource, say in this particular case here, I stored this shape as a member variable and needed to use it again to do another draw call, the shape can reconstitute the WASM object from the serial stream, so it can deserialize itself. So this way, the object doesn't go you don't lose the object. Now, if the object truly does not get used anymore and gets garbage collected, then that's fine too, because the bytes are stored in JavaScript and they just disappear and get cleaned up. So it works out fine that whether or not the JavaScript object stays or goes, it still all works. There are a few little things I've added, like lock and dispose, that will allow you to manually manage the resources to some extent. If, for example, you find yourself deserializing the same object over and over again, you say, well, I'll just lock it and then I'll have to manually dispose it when I'm ready. I think that's just a pragmatic approach, and you don't really need to do that unless you detect some issue somewhere. The JavaScript has a finalization registry extension or option now, which might help. So I might try implementing that at some stage to see how quickly it cleans up objects. So how does the division of labor between the various things go here? Why have I used Haxe? Well, we all knows why you've used Haxe to write a web game. It's because it's the only way to do it. And why have I not used Haxe? I've reused the CPP code from the enemy runtime, and reusing this is very appealing because it's well understood, and that way the results are actually almost identical to the desktop results. So it's a question of code reuse and use what's already there rather than rewrite things from scratch. All right. The next use case is I call it the CYENCY server. I've been doing a bit of machine learning work. Here is a map of Australia's with some predicted mineral zones. Most of the machine learning work these days is done in Python. Now, Python as a language is not particularly fast, but the libraries generally allow you to do a lot with a single call. However, Python has a problem, multi-threading. Its global interpreter lock prevents concurrency beyond a certain point. It does allow some, and it has some multi-process extensions as well that also can be used, but not so great on Windows and in notebooks. So I've come up with a Haxe-based solution here. Python also has these Jupyter notebooks, which provide a REPL that can aid experimentation, particularly when you have want to load a large data set at once and then try out different things. The data does not need to be reloaded. However, it can also lead to errors using these notebooks when the exact procedure or the exact processing sequence is not easily reproduced. So it's tempting to jump in there, make a few changes, run a few things, go back, change something else, run again, then you get a good result and you go, oh, what did I do? Whereas if you've been changing a script and rerunning the script each time, when it works, you've got the script there. But if you have a script, then it can take quite a long time to load, 64 gigs of data or something like that. So there is a bit of a problem. And even though most of the machine learning stuff is done on a GPU, the CPU is still responsible for feeding data to the GPU. And if you're not careful, this can become the bottleneck. So the solution is what I call the CYENCY server. It's a simple server written in Haxe that does the data augmentation and feeding to present the data into the Python machine learning process. The Haxe process loads the data into a C++ generated back DLL, and then serves batches of randomized data to the Python code using efficient multi-threaded code. The data are transferred using a socket to send shared memory buffer handles, which are then decoded on the Python side and can get at the data using a zero copy dereference. So this has the twin benefits of low CPU usage, that is maximum GPU usage, and isolating the loading into a single initial process so that you can do a one load and then share the data between multiple notebooks, multiple runs, or multiple scripts. And it's all runs at full speed or without having to wait for the startup delay. Most of the data processing routines that I use for the data augmentation are fairly simple and along the lines of color transforms or rotations or scales or flips. And I'd already written most of these routines for some of the desktop image processing software I had. So how does the split for this particular one look? Why have I used Haxe? Well, Haxe network code provides an easy way to implement the server. The callbacks and the functional aspects of Haxe I find are very satisfying for writing server-style architecture. And why I have not used Haxe for the whole thing? Well, performing machine learning tasks is Python is very well supported, and you really just can't beat it. So you can grab a piece of Python code and paste it into a small file. It can be up and running in no time. And the Jupyter notebooks are great. You can do graphs and displays and all sorts of things in there as well. So I don't really want to move away from them. And I already had the C++ code to do some of this stuff, so it really wasn't that much additional effort. So the split is that this project is mostly Python with a bit of a C++ engine and a smallish layer of Haxe on top. So this project is actually not one of mine at all. I just bring it up to try to steal some of the glory. The Haxe bindings for the Unreal Engine. So I haven't worked on this. If you look at Dan's Twitter handle there, he's got a stream of some of the development that they've done at Proletariat Games, and you can check out their GitHub page at that link too. And just from their GitHub page, why they've used Haxe is that Haxe compiles directly to C++ for fast runtime performance. There's full access to the Unreal C++ API, including delegates and lambdas, full support for U-class creation, subclassing, and blueprints, and fast compilation using HXCPP's virtual machine Sepia. The Sepia target allows you to either run the whole application as a basically bytecode, or to run plugin style little programmettes written in Sepia that run within a larger CPP runtime. So, why Haxe? I think we just outlined that. Good, fast, and it works. And, why not Haxe? The Unreal Engine is already written, so we can just use it. And, do you really want to go around and write a AAA game engine in Haxe when you can already use what's there? And the division of labor for this one is pretty sweet. I didn't have to do anything. So I guess that's the main guts of this talk. Is really just keep looking for ways to use Haxe, because there are plenty of interesting things you can do out there. But also look for ways of using what's already there and not necessarily feel the need to rewrite everything in Haxe. All right. that's my talk.
Thank you very much. We had one question about what does the depend metadata do. I'm not sure. It was quite early on, I think.
Yes. So the depend metadata basically goes that if the file changes, then at the top here, if the file changes, then the CPP file the generated CPP file needs to be recompiled. So that might be, if you have a header file that you actually is not like a system header file, but one that you've changed, it just adds that dependency to the build file.
Right, I see.
All right. Do we have any other questions?
Oh, we don't at the moment. So I think that's it. Thank you very much.
All right, thank you.
Thank you so much.
And we'll take another break, and we'll be back in about 5 minutes. See you later.